In today's video, we're using R to determine if practitioners should use 1, 3, or 5-day metrics to track the fatigue of their athletes. So we have three main objectives from today's video. Should we use moving averages to monitor athlete load? How can we use R to determine the relationships between 1, 3, and 5-day metrics? And how can we use the patchwork package to graph side-by-side plots? The first thing that we're going to do is use the group by and mutate functions to create 3 and 5-day rolling averages of our RPE and distance. We are going to use the group by function first, so we're grouping by the athletes' names, and then we're going to mutate, so we're creating a new column. We're creating multiple columns, but we're creating 3-day RPE average. We're using the rollmean function of RPE over a 3-day span, and we're aligning by right, so it's taking the current day and then the previous 2 days. We're doing that for several metrics as well as for 5-day RPE average and 5-day distance average, where the roll mean is looking at a k equals 5, so 5 days of data. The first thing that we're going to do is run a linear model looking at the relationship between 1-day RPE and 1-day distance. When we run this linear model and we look at the summary of the model, it returns a lot of data. I've gone ahead and written out some of the most important data points that we're interested in. So we're looking at the residuals of our day 1 linear model, and we're particularly interested in the adjusted R-square, which is showing the correlation between distance and RPE. So we see that there's a 0.67 correlation, so a fairly strong correlation between 1-day RPE and 1-day distance. And then we're also looking at the residual standard error of 0.6869, so how well the trend line fits the data. We can also look at a histogram of the residuals to show the distribution of our trend line. So when we look at it here, we see a slight leftward skew, and we are able to see that we have a range from -4 to +2. We're going to go ahead and run the same thing for our 3-day RPE and 3-day distance. So when I run these two lines and run the summary of the 3-day model, again, I've gone ahead and plotted some of the important features that we want to take a look at. Our R-square is still, it's a little bit larger. Our adjusted R-square is 0.67, 0.675, so a little bit larger. And then the residual standard error is actually smaller, and it's at 0.3793. So what that tells us is that there's a better correlation between 3-day RPE and 3-day distance, and there's a better fit to the trend line. And we can also take a look at the histogram of residuals for this one as well, and that will show us the same thing. So looking at the histogram of 3-day residuals, we see that there's a tighter distribution as well as a smaller range. So instead of -4, it's -1.5, and instead of +2, it only goes up to +1. We're going to do the same thing for our 5-day RPE and 5-day distance, running a linear model and then looking at the summary of that linear model. Our adjusted R-square actually goes down on our 5-day RPE and 5-day distance average. So it was 0.67, now it's dropped down slightly to 0.65. It's still a strong correlation, but it is interesting to note. Although our R-squared has gone down, our residual standard error has continued to drop. So that means that there's a better fit of the trend line, even though that the correlation between 5-day RPE and 5-day distance has decreased slightly, the trend line is a better fit. Again, we can take a look at the histogram of residuals for our 5-day linear model, and we see that in fact there is a better distribution around the median, and there doesn't seem to be any skew. So what that tells us is that using a 5-day moving average has the smallest standard residual error, and that better accounts for any day-to-day variability or outlier data points. However, because our adjusted R-square slightly decreased from our 3-day to our 5-day linear models, practitioners may be warranted by using a 3-day linear model. We can even use ggplot to plot the residuals from our 1, 3, and 5-day linear models. So calling on our 1-day linear model, we're looking at the fitted and the residuals. We're using a geom point, so we're looking at a scatter plot, and then we're going to draw a horizontal line on the y-intercept where the color is red. So when I run that line there, we can see our graph here, and then we're going to do the same thing for our 3-day, where we see a tighter fit around our y-intercept there, and then the same thing for our 5-day. If we want to plot these graphs side by side, we can use the patchwork package, and that will allow us to do that. So we'll call the first graph P1, we'll call the second one P2, and the third one P3. And we'll assign those plots those names, and we'll run those lines of code again, so it assigns them the names P1, P2, and P3. And then all we're going to run is P1 plus P2 plus P3, and that's going to return our graph side by sides. And we can zoom it in here, and it shows it a little bit better here, and we can actually take a look and see that our 5-day fitted model is more fitted than the other two. We can also use ggplot and patchwork to compare the 1, 3, and 5-day linear models. So we're going to create 3 scatter plots, all 3 of them with trend lines, and I'm adding the x limb and y limb so that the graphs, the x-axis and y-axis, are consistent for all 3 plots. So when I run these 3 graphs here, and then again P1 plus P2 plus P3, it gives us a returning graph, and I can go ahead and zoom on here. And this just shows again that using a 5-day distance average and 5-day RPE average shows the best fitted line. What we need to ask ourselves as practitioners is how this affects our ability to predict injuries. We're going to run the same lines of code as above, but we're adding one a little bit, which is color equals injury illness. So that's going to color our injured or sick athletes in a different color. So when we run these blocks of code and then run P1 plus P2 plus P3, and zoom in on this plot here. Looking at these plots, we can see that compared to our 1 and 3-day, that our 5-day RPE and 5-day distance average has the closest fit between our injured and non-injured athletes. That shows us that using a 5-day distance and 5-day RPE average is probably going to be the best bet for predicting injuries in our athletes. In closing, practitioners should utilize at least a 3-day RPE and 3-day distance average to better monitor the fatigue of their athletes, with a 5-day RPE and 5-day distance being the best option.